Welcome back to the last event at the Oxford University Scientific Society this term. In fact, this whole academic year. The past year has been challenging and extraordinary for many of us, and to our audiences, I am more than glad all of you have stuck around with the Scientific Society this term. This week, one of our committee members, Alexandra, has invited Dr. Vicky Hamilton from Boulder in the United States to speak about asteroid Bennu. I will freely admit that I do not know much about asteroids, but I look forward to learning more about the topic in the next hour. The floor is all yours, Vicky.
Thank you very much. Thank you all for inviting me to speak with you today. I'm really excited to talk to you about the composition of asteroid Bennu and what we might expect to find from the returned samples. And I also look forward to your questions. So to give you an overview of what I'll be talking about today, I'm going to talk first about the OsirisRex mission objectives. I don't want to assume that everybody's familiar with the mission. Similarly, I'll give a very brief overview of what are Carbonaceouschondrite meteorites. Then I'll talk a little bit about how we chose Bennu as the asteroid that we wanted to visit and give you a little bit of information about the spacecraft itself and the instruments it carries. And then I'll spend the bulk of the remainder of the time talking about some of the science highlights from the entire mission, but with a particular focus on the composition of the asteroid. As we get towards the end, I'll talk a little bit about the touch and go sampling event, what we call TAG, and then conclude with what are some predictions for the sample that will be returned to Earth in 2023. So OsirisRex is an acronym. It stands for Origins, Spectral Interpretation, Resource Identification, Security, Regolith, Explore. So obviously OsirisRex is a lot easier to say every day. The reason that this mission exists is because primitive asteroids like Bennu are time capsules. They contain a record of what was happening in the earliest days of our solar system over 4.5 billion years ago. So the first thing we want to do with this mission, the prime objective that everything else revolved around, was collecting and returning a sample of a carbonaceous asteroid that is not a meteorite. And I'll talk in a minute about why meteorites aren't enough for this. But we wanted to get this pristine solar system material from the surface of a carbonaceous asteroid and return it to the Earth for study. Our target quantity of sample to be returned is about 60 grams. I don't know about sugar packets in the UK, but I know in the US, this is about 30 little sugar packets that you might find in your local restaurant. The other objectives of the mission are to do things like map the asteroid's composition and geology. So for those of you who may be in geosciences, you'll know that it's important to have context for any sample that you go out into the field and pick up. And so we need that context. And we know that we can't sample the whole asteroid, so we want to make sure that we understand exactly where our sample came from, how it might differ from other locations, and just generally understand the compositional diversity exhibited by an asteroid of this type. Another factor here, and this kind of goes to the security aspect, is that we know that the orbits of asteroids change over time due to things as seemingly inconsequential as solar pressure. And so because those asteroid orbits change over time, asteroids in Earth-crossing orbits can become more or less hazardous to us over time if their orbits change to take them further away from the Earth or closer to the Earth. And then finally, we also wanted to do something very sort of straightforward, which was compare observations at the asteroid to predictions we had made from ground-based telescopic observations in order to give us more confidence in what we are able to say about hundreds, if not thousands, of other asteroids based on similar observations. So the timeline for the OsirisRex mission is shown here at the bottom. And so we actually first wrote the proposal to NASA for this mission in 2010 and were selected for flight in 2011. And from then until 2016, we were busy designing and building the spacecraft. And so we launched in September of 2016, swung by the Earth a year later, and then arrived at Bennu in late 2018. So since then, we had been in asteroid operations until just a few weeks ago. We collected our sample last October, and then we departed the asteroid on May 10th for the return to Earth. So you can see kind of where we are in this timeline. And now we have to wait until fall of 2023 for the sample return to occur. And I'll talk a lot about that at the end in terms of what's involved with that. And then the very final phase of the mission is actually the sample analysis phase, once we have the sample back in the labs and can really test all the hypotheses we've developed in our time at Bennu. So for those of you who may not be familiar with meteorites, and specifically a group of meteorites called Carbonaceouschondrites, these are carbon-enriched stony meteorites. So they have very little to no metal in them, and their parent body was never melted. And the term we use for that in geoscience is differentiated. So Earth is a differentiated body. It's got a core, a mantle, a crust. The parent bodies of these carbonaceous chondrites never went through the process of developing that stratification. They formed very early on in the solar nebula by sedimentary processes. So little bits and pieces literally getting kind of glued together. And they contain a particular feature called chondrules, which is where the name chondrites comes from. And these chondrules are solidified droplets of silicate magma, so of liquid material. Now, the meteorite on the right, Orgay, is an example of a carbonaceous chondrite. One of the things I like about this image is that it shows just how fragile some of these meteorites really are. This particular one has been altered heavily in the presence of water sometime in the early solar system, and that makes it especially fragile among this class of meteorites. They are also, it's possible that in one direction, these kinds of chondrites can become aqueously altered, so altered in the presence of water, but in a different direction, they can also be heated. And that causes recrystallization of minerals and a different mineralogy. So there's a whole range of compositions and processes that have affected these particular meteorites. But that said, they're all comprised of silicate minerals, oxide minerals, carbonates, and sulfides. And they also, as I mentioned before, contain organic compounds, which is one of the things that makes them interesting. It's like, what was the early inventory of organics in the solar system? Of particular interest to our mission is the fact that, as I said, some of these have been aqueously altered. And some of them contain up to 22% by weight of water locked away in minerals. And so Orgay is one of the groups that has this characteristic. So the minerals shown at the bottom, olivine, serpentine, magnetite, and pyrite, are examples of silicate minerals, the olivine and the serpentine. Serpentine is basically what happens when you alter olivine in the presence of water. You add water to the mineral structure and you turn it from olivine into serpentine. Magnetite is an iron oxide, and then pyrite is an iron sulfide. So these are just common terrestrial examples of minerals that are found in these meteorites. So then the question is, well, okay, so we have these meteorites, why aren't they good enough? And part of the problem is that we don't know where they came from. We can't tie them back to any particular object. There are only a very, very few kinds of meteorites among all of the meteorite types we know about that we think we might know where they came from. But carbonaceous chondrites, we don't have that record. And so we need to get a sample that has some context and from an object that we can understand. So that leads us to Bennu. And so I'm about to show you an animation that starts off in 1995 with the number of known asteroids. And then as the animation proceeds, you'll see things, little spots flashing up in white. Those are asteroids as they're being discovered. And then in red, they will get classified as being Earth crossing, and so potentially hazardous. Yellow ones are Earth approaching asteroids. And then the green ones are everything else, things that aren't really encroaching on the Earth's orbit. And so as you see that build up, you see that that's pretty much the main belt of asteroids. As time goes forward, this animation goes all the way through 2010, which, as I said, is when we actually proposed this mission. So this was the entire inventory we had to work with at the time when we needed to select a target. So we were focused on these Earth-crossing asteroids in particular. And what you can see here is that at the end of the animation, at the lower left corner of the animation, it says 2010, 530,091. That is the total number of asteroids we had to choose from at that time. So the question is, how did we possibly get all the way down to a single target? So we'll start out actually on the right-hand side of this slide, which is at the bottom of that pyramid is that over 500,000 asteroids that were known at the point in time we had to design this mission and figure out where we were going to send it. So we did, as I said, target the near-Earth asteroids. So that cut way down. Everything on the main belt was just out of consideration right away. And what we ended up with was about 7,000 near-Earth asteroids. Now, because this mission needs to go to the asteroid, collect a sample, and bring it back, we needed the asteroid itself to have an orbit that was optimal for us to be able to go there and get back. So that, again, significantly cut down the number of asteroids we had to choose from to just a little under 200. Now, we also needed to think about the fact that when we're at the asteroid, we have to be able to conduct operations with a spacecraft around it. So we can't have a 10-meter asteroid. That's not really going to be very useful, and it's not going to be easy to sample. So we stipulated that the asteroid we were going to target needed to have a diameter greater than 200 meters so that we had a reasonable way to conduct spacecraft operations around it. So now we're down to 26. That's almost, countable on hands and toes, right? Or fingers and toes. And then this last criterion is the most important one, and that goes back to our Carbonaceouschondrites. We wanted a carbonaceous asteroid. And so out of those 26 that met all the other criteria, there were only 5 that were carbon rich. And Bennu is the one we selected. So as a point of interest, for those of you who are familiar perhaps with the Hayabusa 2 mission flown by the Japanese space agency, they targeted one of the other 5 called Ryugu, and they just returned their samples from Ryugu back in December and have been busily analyzing them ever since. So asteroid Bennu is depicted in a shape model on the left. The shape model is what we knew of Bennu, or thought we knew of Bennu, before we got to it. These are based on radar measurements from the Arecibo Observatory, which sadly is no longer functioning. But you can see how big Bennu is compared to some structures that you may have experienced either in Europe or the US. It is what is called a B-type asteroid, which means that it has a blue-sloped visible spectrum. Bennu has a rotation period of a little over 4 Earth hours, and a year at Bennu is a little longer than an Earth year. Its mean density is particularly interesting. It's only about 1.2 grams per cubic centimeter. For those of you who may or may not be familiar with sort of normal Earth rocks, they're closer to around 3 to 3.2 to 3.3, depending on what kind of rock you're talking about. So this is a very underdense object relative to most rocks on the Earth. And then the other interesting characteristic about it is that the average albedo is only about 4%. That is darker than a charcoal briquette that you might put in a barbecue. It is incredibly dark object. So the OsirisRex spacecraft carries a suite of science instruments designed to address a number of different questions and make a number of different measurements at different wavelengths across the electromagnetic spectrum. So I will start on the left with Rexus there at the top. This is the student imaging experiment that is an X-ray spectrometer for determining elemental chemistry. As we move next over, you can look at that little tiny swath of the spectrum that our eyes are sensitive to, visible light. And that is expanded out down near the bottom to OCAMs, which is the OsirisRex camera suite. That's actually 3 different cameras for looking at Bennu from very far away in orbit, and then at the sampling scale when we're approaching the asteroid for sampling. Just beyond that, at 1064 nanometers, we have the OsirisRex laser altimeter. So this is a topography mapping instrument that fires a laser and looks at the return time to gauge distance between the spacecraft and the surface. And then up above the EM spectrum there, you see OVIRS and otis. And these are our compositional spectrometers that I'll talk in a little more detail about. OVIRS is the OsirisRex visible and infrared spectrometer, and otis is the OsirisRex thermal emission spectrometer. And so OVIRS covers the parts of the visible and the near infrared, and otis covers the thermal infrared. And then at the furthest wavelengths, we use our telecom system for science as well to do radio science. So here's a picture of our launch in September of 2016. I was fortunate to be able to attend the launch. This was at Kennedy Space Center in Florida. Absolutely stunning day, beautiful launch, really, really amazing experience, and hope you all find a way to experience a launch someday if you haven't. It really is quite a sight to behold. And about 2 years later, we arrived at our target, Bennu, and the image on the left shows you what we saw from afar. And this was quite unexpected for us. We were a little bit shocked, to be quite honest, with how many rocks there were on the surface of Bennu. And the image on the right shows you just how rocky that surface is. If you've ever seen pictures of an asteroid like Eros or Itokawa taken close up from a spacecraft, you'll know that they're not covered in these kinds of boulders. The boulder, sort of that brightish, large-ish, brightish boulder just lower left of center is about, oh boy, I'm going to do it in feet, and I apologize, about 27 feet across. But it gives you a sense of just how large everything on this object is. And immediately it caused us to worry about where are we actually going to be able to touch this thing and get a sample that we can collect with the collector that we brought with us. And so I'll touch on those issues in a moment. So one of the first discoveries that we made was one of the most unexpected. So we generally think of asteroids as being dead rocks, but Bennu really surprised us in the very earliest days of the mission. So the image on the right is one of my favorite from the mission. It looks like this beautiful picture of the limb of the asteroid and the star field off to the right. But it turns out those aren't all stars. And this is one of our resident astronomers who was trying to look for small satellites at the time as potential hazards, looked at that and he was like, I don't recognize those stars. And what we figured out was that, in fact, they weren't stars. Bennu was actually ejecting particles on a fairly regular basis. And these rocks are anywhere from 1 to 10 centimeters in size. And they generally don't escape Bennu's ridiculously small gravity. They still usually fall back down onto the surface. So they're all still there, but it does mean that there's a new process going on that we didn't really understand before. Now we think these processes, the particles might be getting ejected by thermal fracturing. The surface of Bennu goes from being, a couple hundred Kelvin to, 330 Kelvin or something like that over the course of 4 hours. So there's considerable thermal effects going on. Accompanying that could be the release of water from minerals. We also considered whether micrometeorite impacts were causing these ejection events, but we think it's probably most likely some sort of thermal fracturing. Now, mass loss ejections on a much larger scale have been observed previously. A series of, or these are commonly referred to as active asteroids. They used to be called at one point main belt asteroids, but we hadn't seen anything on small scales like this. So this means that whatever processes are going on, they're occurring at multiple scales of asteroid size. But this process, ultimately contributes to how asteroids evolve and how they're ultimately destroyed as these materials do get shed. Even though for this asteroid, it's not many of the particles, there's still particles over time, geologic time, that are being lost and changing the makeup of the asteroid. So another discovery was that we had very unusual thermal properties, and these appear to be tied to two populations of rocks. So there's a property called thermal inertia, which is the ability of a rock to hold on to heat. So the way to think of it is, I'm a rock. The bigger I am, the denser I am. When the sun comes up, I get heated up, but it takes me a long time to heat up, as opposed to something like sand, which would heat up very quickly because it's small and the conductivity is very efficient. But then once I do heat up, I'm also very slow to cool down. So a big rock at night stays warm, whereas sand cools off quickly. If you've ever been to the beach, you've experienced this in all likelihood. Now, we had thermal inertia measurements from the Spitzer Space Telescope for Bennu before we departed. And based on those results, we had predicted that the particle size on Bennu was somewhere on the order of a couple centimeters in mean size. So we figured there would be a lot of material smaller than that, and then a few things larger than that. And normally, high thermal inertia, so the red areas on the graphics on the left, would be associated with bigger, bulkier, rockier materials, and sands and dust and things like that would have low thermal inertia. They don't hold on to their heat very well. But if you look at those figure 2C and 2D boxes, they correlate to the two images on the right. And what you see is that the thermal inertia trends are exactly the opposite of what we would normally predict. So in the top right figure, you see this big exposed slab of rock, but it's got low thermal inertia. On the other hand, the figure below it shows a pretty rocky area, but not any big rocks, mostly smaller rocks, and yet it has a really high thermal inertia. And the way we've interpreted this is that, unlike, for example, the case on Mars, where thermal inertia is generally very well tied to the size of the rocks, and the rocks have a pretty common density, in the case of Bennu, we had to take that apart and think about it in a different way. And the interpretation that we have is that the reason these big rocks have low thermal inertia is because they've got higher porosity. So their ability to retain their heat is reduced by that porosity. So that was one unexpected result. Another discovery is that Bennu is both old but also dynamic. So we know asteroids are very old. We know they never got incorporated into planets and that they basically became sort of theoretically dead objects very early in solar system history. But the global map on the top there in with the rainbow colors shows you the planform layout of Bennu. And you can see, especially through the equatorial regions, that there are these ring-like structures that we have interpreted as being old, ancient impact craters. And so we know that the surface of Bennu is, at least based on these craters and their sizes, on the order of 1 billion years old. So Bennu is what is called a rubble pile asteroid. We think it was formed from the collision of Bennu's parent body with another parent body, and then recreated as this pile of rubble that's being loosely held together. But this pile of rubble that we call Bennu is still quite old. The boxes on that diagram highlight very small craters on the surface of Bennu. And these were places that we were looking to consider as places that we could target for our sample collection, because they tended to show very fine-grained materials or very fine particulate materials beneath the resolution of our cameras. And so the one highlighted there in pink, and that occurs sort of near the top left of the map, is the actual Nightingale sample site that we visited back in October. The image on the left is also interesting. It shows another one of these low inertia rocky terrains, but you can see from the arrow in the lower right that it's showing that there are rocks that have basically overridden that big slab of rock. So material is moving across the surface of Bennu. And one of the posited explanations for this is seismic shaking, that Bennu undergoes adjustments and readjustments. It changes slightly as orbital forces act on it, and that is enough to cause rocks over geologic time to move across the surface. And so that changes what we're seeing and how we interpret it. Another discovery that we made was what we call brecciated rocks. And so a breccia in geology is a rock that is comprised of many other pieces of rock. And those pieces of rock have all gotten glued together to create this new rock called a breccia. And so these are two examples. I'll start with the one at the lower right. And so the zoomed in view is of a 21-meter boulder on the surface of Bennu. And if you look at that thing right in the object of the big red box, you can see that there are different sort of blotches of color. There are some light colored zones and some darker colored zones. And that's how we identify this as being a breccia. It's clearly one coherent rock, but it appears to be made of many pieces of other rocks. The example on the left is the same sort of thing, but in this case, it looks like that breccia has now disaggregated or fallen apart into its original constituent components again. So there are processes that are acting on these old asteroids, or even very early in the solar system, to form these breccias, but then things happen over time to cause them to break apart again. We don't have anything like this in our meteorite collections on these kinds of physical scales. We see brecciation in meteorites, but it's happening over scales of millimeters to centimeters. We have no idea that we would expect to see something tens of meters across like this. Okay, so let's talk a little bit about composition. This is my specialty. I am a geologist by training, and I use infrared spectroscopy to determine the composition of surfaces on planetary objects like the Earth, Moon, Mars, and Bennu. And so I'll talk just a little bit about what are the instruments that are collecting these data. I mentioned OVIRS is a visible infrared spectrometer. It measures from about 0.4 to 4.2 microns. During our global mapping phase, it has a ground resolution of about 20 meters per spot. So that's 20-meter diameter spot on the ground. And then the OsirisRex thermal emission spectrometer is also a point spectrometer. It's got heritage from some Mars missions. It measures longer wavelengths than OVIRS does at slightly lower spatial resolution. So one of the first compositional discoveries we made, actually, was the discovery of materials that didn't seem to belong. We found in about a half a dozen locations across the surface, there were these incredibly bright looking boulders. So I mentioned at the beginning that Bennu has an albedo that's generally around 4%. These have albedos of 12 to 14%. So they're incredibly bright relative to the background of Bennu, which is how we noticed them in the pictures. And then we really had to work hard to extract spectral data because, as I just said, our spectral data are at much, much lower resolution than the size of these little rocks that are only a couple meters in size. But we were able to do that. And when we did that, we looked at the spectral features in the near infrared and observed that there were absorption bands near 1 micron and 2 microns. And that is a classic signature of the mineral pyroxene. And when you plot the positions of the 1 and 2 micron bands relative to each other, like on the top right plot, what you find is that you can actually distinguish something about the chemistry of that pyroxene. So pyroxene is what we call a solid solution material or mineral. It has a range of compositions, and the primary solid solution is exchange of magnesium for iron. There's also plus and minus calcium in this particular silicate mineral. But the point here of the figure is to show you that we can plot the Bennu pyroxene compositions and determined that they are relatively low in calcium and probably more enriched in magnesium. And this is consistent with a series of meteorites called howardite, eucrite, diogenite meteorites, or head meteorites. And I mentioned very early on that we know where very few meteorites come from. These particular meteorites, we actually have evidence that they probably originated on the asteroid Vesta. So these little boulders sitting around on Bennu really provide evidence of interaction between asteroids over time after the formation of planetesimals. We don't know whether these were delivered directly to Bennu, like meteorites are delivered to us, or whether this happened as part of a collisional event. But it was a very, again, unexpected compositional result. Now, in terms of the bulk of Bennu, the first thing we discovered, I'll talk about the visible near-infrared results first and then the thermal infrared results. When we looked at the visible and near-infrared results, we saw this black spectrum over here on the right. The 2011 spectrum from Clark et al. In red is a telescopic spectrum. So the very first check mark we got was, hey, we actually did a good job of proving out that our telescopic observations were a good predictor of what we would find when we got here. So we made that conclusion. We also, again, observed that we documented this B-type or blue-sloped spectrum, and that there we didn't see any particular features of note out to about 2.5 microns. This can be a property of space-weathered materials, micrometeorite bombardment, solar irradiation, but more and more detailed laboratory measurements these days are showing that space weathering can create blue or red slopes depending on the starting composition and other factors. So we haven't been able to specify what's going on there. But we see this unambiguous so-called 3-micron feature in all of the spectra of Bennu. And the 3-micron feature, for anybody who's familiar with this kind of spectroscopy, is sort of one of your holy grail features. It tells you there's water present. This is a fundamental stretching mode of hydrogen and oxygen, and its position and shape depend on whether you're looking at water or hydroxyl in minerals. And so we knew immediately that we had gotten to a Carbonaceouschondrite asteroid that had water in its minerals. And so we mapped out where the location of this band was, and it is at 2.74 microns. And that allows us to compare to a whole suite of laboratory measured meteorites. Now, only some carbonaceous chondrites have interacted with water, as I mentioned very early on. Some have had exposure to heat and had recrystallization and all that. So we knew that we could immediately eliminate those compositions from consideration. And we compared with the band centers of of what we call Ci and Cm meteorites. And those are distinguished on the basis of oxygen isotope information. But what I want you to focus on the graph on the right is that we've got a bunch of meteorite spectra showing that 3-micron band. And then I've highlighted in blue there the position of the so-called 3-micron band, which actually fluctuates considerably in these meteorites from about 2.8 down to 2.71. And then the Bennu line there shows you the 2.74 position roughly that we see at Bennu. And so what that tells us is important. It tells us that this is among the most altered, aqueously altered meteorites that we've seen in our laboratory collections. It tells us that it's probably dominated by minerals that are enriched in magnesium rather than in iron, and that tells us about its history as well. So these were all very exciting results. But then we got even more exciting than this, which was that we were able to detect carbon-bearing compounds. So out near 3.4 microns, there are a bunch of different spectral bands that are attributable to carbon-bearing compounds. And in this particular case, we're talking about carbon-bearing organics as well as carbon-bearing minerals, and those are referred to here as carbonates. Now, the plot in the lower center of the chart here shows you the actual Bennu data as the dots connected by the straight lines, and then the heavy black line is the smoothed data. And then the colored spectra below those are laboratory spectra. And in this particular case, all of those laboratory spectra are of the mineral carbonate. The different names reflect slightly different chemical compositions of carbonate. Now, the organic signatures, and the thing too here is that organics and carbonates actually overlap in their positions, and so it takes some work to kind of extricate those band positions and understand them. But once we did that and we looked at where the organic signatures occurred across the surface of Bennu, they didn't seem to correlate with anything else. They didn't seem to correlate with rocks, big rocks or small rocks, or high inertia or low inertia, or anything else. And so the best way to explain that is to say that there are simply differences in abundance that we're not sensitive to. They may be recently exposed rocks at the surface or altered differently by space weathering. And so it's a complicated thing to unravel. On the other hand, some of the carbonate signatures, and so those are the ones shown in the colors in the spectral chart there, actually seem to be correlated with centimeter thick and meters long bright lineaments in boulders on the surface of Bennu. And so the interpretation here, and those are exemplified by the figures on the right, is that these are veins. And so these are places in the rock, fractures that opened up during aqueous alteration in the presence of water. The water flowed through these fractures and was depositing these minerals over time to create these veins. Now, not all of the carbonates are associated with veins. Not all of the veins are associated with carbonate, but there are enough cases where we saw this coincidence that we have interpreted these as veins of carbonate in the boulders. And so again, on the scale of centimeters to meters, this is something we have never seen in our meteorite collections. It tells us that aqueous processes were operating over very large distances of meters to even kilometers on the parent bodies of these asteroids, and we've had no evidence for that prior to this. So now we'll move into the thermal infrared and talk for the evidence here of hydrated minerals. If you look at the lower left image, the spectrum in the red is labeled average Bennu, and that was when we were first approaching Bennu. And in this particular wavelength region, we're sensitive to the fundamental vibrations of molecules in minerals. And the positions of the dips in that spectrum are diagnostic primarily, in this case, of silicate minerals. And these are the primary minerals that we find on Earth as the fundamental building blocks of most Earth rocks. And there is a feature, there's a little spike downward between 300 and 400 wave numbers there. That one is attributed to the mineral magnetite, which is an iron oxide. Now, if we take that average spectrum and we compare it to a bunch of Carbonaceouschondrite meteorites measured in the lab, that's what we see on the right. And so the first thing we wanted to do was sort of understand Bennu inside this continuum I've referred to a couple of times now of aqueous alteration all the way to thermal heating and metamorphism. And so the meteorites in color there from Orgay are the most aqueously altered, so they're the most water rich. And then as you move towards the bottom of that plot, the minerals change and don't contain water. And by the time you get to the bottom, that Vigorano sample, there's virtually no hydration left in a sample like that. So we were able to look at Bennu in comparison to these and say, yes, it is in fact most similar to the ones at the top and to the hydrated mineralogies. And so that suggests that Bennu has had extensive interaction with water. But we can take this a step further and we can look at exact spectral features. The position of this peak in the Bennu spectrum, it has a name, it's called the Christensen feature. It has to do with the optical properties of the mineral. But it's a diagnostic spectral feature. And again, it is most similar to the things at the top than at the bottom. This broad minimum here between about 9 and 14 microns, again, is due to silicate minerals. And you can see that the shape is relatively broad. It doesn't have a lot of, detailed structure on it. Whereas as you go down that plot, the structure superimposed on the big absorption is much more detailed. And all of those little wiggles mean things. They're diagnostic of the minerals in the rock. So we see, again, more similar to the things with water, less similar to the meteorites that have been heated. There's another peak out here around 19 microns that is very similar between Bennu and the aqueously altered meteorites. And that peak is gone by the time you get to the sample Murchison and the ones below it. So we really understand that, Bennu really is one of these hydrated compositions, even though there's not a precise match to the ones we've seen. But among the ones that are good comparisons, these all have more than 50% water-bearing minerals in them. So that's an important conclusion to draw from the data. We went and looked at the distribution of various otis spectral signatures across the surface of Bennu. And what we found were that there were basically two variations, and everything else was mixtures of those. And so the figure up on the right, the global average that I was talking about on the last two slides, is shown there as the solid white line. And then these two end member types that we later distinguished from the resolved data are shown as the red and blue lines. And so you can see that they have very, very similar shapes at short wavelengths or high wave numbers. They have very similar shapes at long wavelengths or low wave numbers. But right there in the middle of the plot, there's a big difference in the spectral shape. And in some spectra, what we call type 1 or T1, that band minimum is located at 987 wave numbers. And in the red spectra type 2, it's located at 814 wave numbers. So there's a spectral slope there that is a very diagnostic feature. And so what we did was we literally made a ratio of the band depth at 987 and ratioed that to the band depth at 814 wave numbers. And then we mapped that out across the surface of Bennu. So the figure on the bottom shows you the distribution of the type 2 spectrum, so that red spectrum. And so the red spectrum corresponds to the red areas on the map, and the blue spectrum compares to the blue areas on the map. And so you can see that they occur in geographically consistent areas. It's not just random noise. There's concentrations of these two end members. And so the question is, what does this mean? We also observed that the type 2 spectrum tended to correspond with those low inertia big boulders that we discovered. And so the question is this telling us something about composition, or is it telling us something about a physical property like particle size, which also can affect the expression of mineral bands in spectra? So we went back to our library of spectral features of Carbonaceouschondrites, and we said, okay, let's test the idea that it's composition. So we have a whole new suite of meteorite spectra here. I've got the Bennu type 1 and type 2 plotted at the top. A meteorite called Almahata Sitta has carbonaceous clasts in it. That's the next spectrum down in sort of the brown color. And then our friend Orgay is there again below that. And then as you continue to go down this chart, all of these are aqueously altered meteorites, but the degree of aqueous alteration gets smaller and smaller and smaller as you go down the chart. So it's kind of the same general trend as what I was showing before. So when we compare these spectral features, the peaks and the band minima and where they occur, what we see again is that the Bennu spectra at the middle wavelength region or the middle wave number region, there's really no exact matches among the meteorites. But if you look out to the right and you look at those dotted vertical lines out around 19 and 23 microns or 530 and 440 wave numbers, you'll see some pretty consistent comparisons between the Bennu spectra and the meteorites. And that is, again, consistent with the most aqueously altered meteorites. But the variations that are happening in the middle, those don't appear to be compositional because we don't have anything in these meteorites that has a band minimum out past 12 microns. So we started to think about, it seems like there's something else going on here. In infrared spectroscopy at these wavelengths, if you have a change in that 9 to 15 micron region, you should also have a change at the longer wavelengths. The fact that we don't see that says it's probably not a compositional difference. But we can, from this chart, apply even more stringent compositional constraints and say that there's very, very little anhydrous or dry mineralogy in this rock. And that, again, is confidence inspiring because it means we're trapping early solar system water. So let me go to the next slide. Oops. So now we start to consider dust and whether we might have dust on these rocks that we can't see with our cameras. And we know that when you have a big pile of dust, spectrally, it produces distortions to the spectrum because the dust is smaller than the wavelength of light, and so it scatters the light. And the example at the top right, again, our friend Orgay, this highly aqueously altered carbonaceous chondrite, the white spectrum shows the spectrum of Orgay as a solid. And then when you grind it up into a powder, what you see is the gray spectrum. And you see that the feature, the peak marked CF, has shifted to the left in the powder. The RB, or the Reststrahlen band, it's just a name of a particular band minimum, has also shifted to the left. And in the fines spectrum, or the powdered spectrum, we now see the development of a new feature called the TF, or a transparency feature. And that is the evidence of scattering that is present in fines, where you've got particles smaller than the wavelength of light, or on the order of the wavelength of light that you're looking at. Now, the Bennu type 2 spectra don't show quite the same degree of effect as the Orgay lab samples in the top figure. I should also point out in that top figure, if you look out to the right, you'll notice that the long wavelength spectra aren't very different between those two samples, but the mid-wave spectra really do show those scattering effects. So this led us to think, we're on the right track, but we're not seeing that really well-developed TF, or transparency feature, but it looks like a hint of it. So what we went to was some literature that was a master's thesis where a student took a basaltic rock, so this is a volcanic terrestrial rock, and progressively coated it with increasing thicknesses of dust and measured its spectrum. And that's the lower right panel. So the substrate is the bare rock, and then you can see what happens to the spectrum, how it evolves as you add more and more dust. And so effectively, what we think is happening on Bennu is that what we're seeing is the presence of very, very thin coatings of dust, maybe 5 to 10 microns at most. And so this is actually consistent with the thermal inertia results that we have. The thermal inertia data, that's how well the rocks hold their heat through the course of the day. There are ways to use those data to place constraints on the amount of dust that can be present. And those data say there's not very much dust present. In fact, they don't even need dust to produce their data. But we can see it with the spectrometer because our sensitivity is a little bit different. So we think that this is what's going on. So that was an unexpected result and something we're really looking forward to testing with the return sample. So let's talk about the return sample. How did we select our sample site? And so I talked a lot about how our surface was incredibly rugged and unexpectedly so. We originally designed the spacecraft to have a target ellipse, or the zone in which we felt we could confidently control the spacecraft, of 50 meters in diameter. But there were no areas on the surface of Bennu that were that big without big hazardous rocks in them. So we had to work on the fly to figure out how to reduce our ability to position the spacecraft so that we could be confident it would get to within a 10-meter zone instead of 50. And so we targeted the 4 sites you see here. all named after birds. Nightingale, kingfisher, osprey, and sandpiper. Nightingale became our primary site, and osprey became our backup. So here's how the touch and go sampling process works. We have a big long arm that's about, let's see, about 11 feet long on the mounted to the body of the spacecraft. That arm is extended, and out on the end of it is this sampling head. It has the arm has gas canisters of dry nitrogen gas mounted on it, and they're connected to the sampling head such that when the sampling head makes contact with the surface, the first of 3 gas canisters is released. And that's what you're seeing with those arrows. The gas comes out of the sampling head into the surface, disrupting the surface materials and causing them to flow into the sample collection area. So you'll see that there's little brown flaps there that lift up, and that is meant to close back down to keep the sample inside once it's been collected. So now here we will see the actual tag event as captured by our cameras. And I'll just let this run through a couple of times. So we never actually land the spacecraft. The arm contacts the surface, the gas bottle releases, and then the sample is collected, and a few seconds later, the spacecraft backs away and returns to a safe orbit. And I'll just let this run one more time. You can see that there's a tremendous amount of material liberated in this process. It's flying everywhere. But it gave us a lot of confidence early on that we had actually collected. So after this tag event, after we had backed away safe orbit, one of the things we wanted to do was try to verify that we really had gotten a sample. So the picture on the left is a picture of the sampling surface of the sample head. So that big flat round area with all the little sort of silvery discs on it, that's the part that contacted Bennu. The sample then goes into that carved out area in the middle and gets trapped in the outer ring there. What you see in this picture, though, is that there are particles hanging around the sampling head, and that really caused us concern. And if you look inside the sampling head there, kind of in the shadowy area, but to the left of center, you'll see there's sort of a curved area. And that is the flap, the mylar flap that was supposed to close and keep the sample in. And so our interpretation of these images, and we had many more of this type, was that we had collected so much material that in fact the mylar flap was unable to close and we were actually losing material. And so this actually turns out to be a sequence of images. And if you pick any one of the particles in this image, especially to the left-hand side, you can see those particles moving away from the sampling head. And so we became very concerned that if we didn't stow the sampling head very quickly, that we would lose more material. Now, we had additional observations or measurements planned. We were going to spin the spacecraft to do a moment of inertia analysis to see how much sample we had collected. And everybody said, no, 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 we can't do that. We'll be flinging sample out all over the place if the flaps are not closed. So we spoke with the authorities at NASA headquarters and said, look, here's our concern. We think we got a lot of sample, but we're clearly losing some of it. We would like to stow the sample in the return capsule as quickly as possible. Can we go ahead and do that without guaranteeing that we've collected the 60 grams we targeted? And NASA said, yes, it's more important to preserve what you've got. So the image on the right shows you a side view from what we call our SAM cam, or our stow cam, our stowing camera. That is actually the moment that the arm tipped back and put that sampling head into the return capsule. So the bottom brown part of that image is the back side, the back heat shield of the capsule. and the diagonal object in the upper left is the top of the capsule that has the heat shield on it. So sample return. We are now in the process of bringing the sample back. As I said, we left Bennu on May 10th. When we come back, OsirisRex, the spacecraft, will be on a direct impact trajectory with the Earth. And just a few hours before that impact would occur, we will release our sample capsule. You can kind of see that schematically at the far left. That white object in front of the spacecraft is the sample capsule. And then as soon as the capsule is released, the spacecraft will do a burn to divert it from colliding with the Earth and send it into solar orbit. The capsule then will come down through the atmosphere and is going to land in the state of Utah in the west. There's a military test and training range out there. And so it is a wide open area with very few hazards for the capsule. Other spacecraft missions have returned capsules like this to this location, notably the Stardust mission and the Genesis mission. And so the capsule will get to a certain altitude, it will pop a parachute to slow it down, and then it will land on the surface where the team, the OsirisRex team, will go and retrieve that capsule. The capsule will be taken without being opened back to Johnson Space Center, which is in Houston, Texas, and that's where the sample will be opened and examined. So this is my last slide. And so I think based on everything I've talked to you about today, it's a lot of content, a lot of information, a lot of things. But from this information, we can make a fair number of predictions about the sample that we expect to get back. So first of all, we expect to get a lot of material. We nominally were targeting 60 grams, but we're hoping and thinking that based on the measurements we do have, this could easily be 150 grams or, give or take, 100. Either way, we're confident that we got our target amount of sample and potentially a considerable amount more. Now, the image on the right is a fun one. It is an artist's conception with a sort of semi-transparent view of the sampler head, just so that you can kind of see where sample would be collected inside this sampling head when we pop open the return capsule. Based on the data that we saw at Bennu, we think there's going to be at least 2 lithologies based on spectral reflectance, as well as the texture of those rocks, the big dark boulders, and then the smaller rocks that have higher inertia and are a little bit lighter in albedo, although all are still very dark. We have reason to believe from the spectral data and again the imaging as well that we'll see both solid samples as well as some fine particulates, maybe not as many fine particulates as we might see from another asteroid, but we still think those fine particulates are going to be there. I didn't talk about this a lot, but we've seen different rock shapes that range from things that look very flaky to things that look much more solid and more coherent. But we still expect overall the rocks to have a high porosity because of those thermal inertia measurements that were opposite to what we expected. Based on our compositional data, we do think that the sample is going to be dominated by minerals that contain water and hydroxyl, and that they are going to comprise more than 90% of the silicate minerals. We also saw evidence for magnetite, carbonates, and organics in all of those samples. So this is great because these are all the things we went to Bennu to sample and collect. If we're really lucky, maybe we'll actually find a fragment or 2 of those materials that we think come from Vesta. It would be really exciting if we see that. And if we see them as individual particles or if we see them as being embedded in some of these brecciated rocks. And then again, based on the spectral differences, we can say the spectra of Bennu are similar enough to carbonaceous chondrites that we know we've got carbonaceous chondrite, but they're different enough for us to postulate that maybe they're not exactly represented in our meteorite collections. And this is a new type of carbonaceous chondrite. And so by virtue of having these big giant carbonate veins, these big boulders, these large breccias, that suggests to us that maybe Bennu is not typical of what we have in our meteorite collections. And that's maybe partly because our meteorite collections are biased. Anything that makes it to Earth as a meteorite has to survive an impact on its parent object. It's got to transit the solar system. It's got to get through our atmosphere. It's got to land on our Earth, and it's got to get found by us. And those are all actually kind of remarkable steps each way through. So it's not at all unlikely or unthought of that there are certain kinds of meteorite material that get screened out by the impact process on Earth. And so we might maybe just have something really unique here in the sample from Bennu. So with that, I will invite you to continue to follow this mission. We're going to be working now on our sample analysis plan and continuing to update the public at conferences and through publications about what we're finding. And I'm happy to take any questions you have, and thank you very much for your time.
Well, thank you ever so much for that brilliant presentation. I think you just about hit the 1 hour mark, so that's brilliant timing. I have to admit I don't know a lot about asteroids, but I've definitely known more in the past hour than I ever did before. Right, with that, we'll get started with questions. Audience, if you have any questions, please do post them in the chat. We will collect them and read them out. But for now, we will have one of our prepared questions in the captions below. Right, so here we go. Could you explain how thermal fracturing leads to rocks being ejected from Bennu?
I can try to. This is not my expertise, but I think the idea is if you think about it, if on Earth you think about processes of freeze thaw, that over the course of a winter season, for example, roadways can you develop potholes and cracks, and then water seeps into those, and then when the water freezes, it expands into as it becomes ice, so that expands the fracture. We're thinking that it's something similar, but happening now on a molecular level within the minerals. And so you have a mineral structure, which is a regular pattern of molecules. And some of the molecules in there are water. And so if over the course of the Bennu day, that water is potentially maybe not freezing and thawing exactly, but it's changing its thermal condition, and it's expanding and contracting, that might result in sort of very, very tiny catastrophic flexes of these minerals that might be just enough to eject some of these particles off the surface.
Right. I think my our editor muted me for a second, so I was just sorting that out. But I think that's a good explanation. Thinking about freeze thaw, that's definitely an phenomenon we can all relate to. I think I learned about it in my GCSE geography, so that was I will count that as a very detailed explanation. We'll have one or perhaps two other questions. I'm just conscious of the time. But yes, we'll have the next one up in captions, please. What's the relationship between the material that made up Bennu and the material that made up Earth?
That's a great question. The thing about the Earth is it went through this process I referred to very, very early on called differentiation. And so differentiation is basically the processing and reprocessing and then reprocessing again of all the materials that were originally present in the early solar system. And so the reason we can't use the Earth to tell us about everything that was going on at the time our solar nebula was around and our sun was forming and our planets were forming is because the Earth's geology has been reprocessed so many times that it doesn't look like what it started with. But fundamentally, one of our questions is, well, the Earth is still made, as Carl Sagan would have said, out of star stuff. And it's just really reprocessed star stuff. So a lot of what Bennu is made out of is comparable to material and chemistry that we have here on Earth, but it's been much, much less processed. So it really is a much better representation of what were the molecules that were flying around the solar system in the earliest days of our solar system. And why we care about those is because we want to know what was the inventory of organic compounds, what was the inventory of water, Where was that water with distance from the sun? How did we end up here, literally on Earth? Because that inventory, that original inventory of organics and water, is what we have come to believe are the fundamental components of life on Earth. And if we can understand the relationship between what we see here today on Earth and what was happening over 4.5 billion years ago in our solar system, we can start to maybe draw some inferences about, the commonality of life potentially elsewhere in our solar system and even beyond. I hope that answers the question.
I think it definitely does. It makes a lot of sense to start the search where everything hasn't been changed as much, and then see how the following change came about. I remember,
Yes.
as a biologist myself, I remember reading about the primordial soup experiment very, very early on, and that was about how they tried to make amino acids from all the various different kind of material atoms they had available. They thought they had available at the time, and
Right.
perhaps in the future we'll be able to construct a more accurate form of that experiment and see and get some kind of knowledge, gain some insight from that. We'll have one last question, and then we will probably have to wrap up, I think. Right, one last question. How technically difficult is it to land on an asteroid, or not land, but rather just to get attached to, or actually manage to hit an asteroid with the arm that you were describing earlier?
That was a huge technological challenge. And I think if you had showed this asteroid to our navigation team in 2016, they would have all thrown up their hands and said, there's no way we can do this. As a matter of fact, OsirisRex set Guinness World Records for smallest object ever orbited, as well as for, other things related to the operation of the spacecraft around a tiny object. And it really is a testament to the persistence of these teams and their incredibly hard work that once we got to Bennu and saw just how much more complicated it was going to be than we had thought it would be, that we managed to pull this off, and it went flawlessly. But and again, I'm a scientist. I'm not an engineer or an aerospace engineer or navigator, but I know from enough of the conversations that I participated in that this was incredibly difficult. We have maybe become accustomed to seeing things like landers on Mars. And, they talk about the 7 minutes of terror at Mars as you're going through the atmosphere on your way to landing on the surface. But the surface is huge. And while there are always threats and hazards, you're really not trying to target something at the meter scale. And they really had to do that with this mission. And it really was impressive. And they made it look very easy.
I think that's a perfect point to conclude and wrap up this event we had this term. So definitely a lot of effort that's gone into this mission. So I think we'll definitely look forward to the day when we manage to retrieve the sample collected from Bennu in 2023. But for now, this is going to be the conclusion. Again, thank you, Vicky, for joining us from all the way across the pond today. And thank you to all of our audiences, wherever you might be. It also happens to be that this will be my last time hosting you. So thank you ever so much. Next term, Carlos will be leading us, and he will be taking over from me as the president of the society. All the best of luck to Carlos and the new committee team in the upcoming terms. With that, have a lovely summer break, and goodbye for now.